Okay. We want to get to like machines at some point pretty soon. But let's just make sure we understand poly as a category. So poly is the category of polynomial functors. A functor is polynomial if it's a coproduct of representables, at least in here. Polynomial functor from set to set is a coproduct of representables. Polynomial functors and natural transformations between them. So if you have poly between one polynomial functor and another polynomial functor, oops. Well, the work we've done means that we can we know from the first part of the day that we can take this sum out, right? And so this is equal to, or isomorphic to, the product over I in P1. For every position of P, a polymap from Y to the PI to this sum. But that's the same thing as, since this is representable means the Uneta lemma says that we can say that this is just I in P1, and I just take this thing, J in Q of 1, Y to the QJ, and I apply this to, as a functor, PI. But what does it mean to apply it? Well, it means to plug it in for Y. So that's the product over I in P1 of the sum over J in Q1 of P bracket I to the Q bracket J.
So, can I say something?
Yeah.
There's a really important thing to just have. The dependence on the objects of set just disappeared.
Which depends?
Y is just gone now. Y is a variable, which ranges over the objects of set, just went away. That's huge, right? Because it's impractical to do natural transformations from set to set because there's too many components. You got to do a component for every set in set.
Yeah, to figure out how many natural transformations are there from this to this seems very daunting.
Yep.
Like for every set X, I need to, have a map from this sum of products to this sum of products of X. It just seems like too much stuff. But the Uneta lemma says it just kind of got rid of it. Yeah. And just became a set theoretic thing. Yeah. And then, so this is isomorphic to one more thing. Let's just use the distributive law one time. Sum over I in P of 1. No, sum over J taking P of 1 to Q of 1 of the product over I in P of 1 of the product over E in Q of J of I of PI. Okay. Here I really was supposed to write J in sum over I in P, product over P1 of Q1. But this thing is,
Those functions.
yeah, this is the set of functions from P of 1 to Q of 1. So this was kind of supposed to be there, and I just wrote it from memory instead. But this one's kind of nicer in some way. So what happened here is I switched these two, and I told you earlier today how you're supposed to switch those two. Now, which one of these is nicer is up to personal taste. They have different okay, so this one says to choose a map from polynomial P to polynomial Q, here's what you do. You choose for each I in P of 1, for each position in P of 1, choose a position in Q of 1, and, because you're supposed to put an and, for each direction in Q of J, pick a direction in P of I. So it's kind of like you have this P thing, and it's got two parts, and this Q thing, and you have two parts, and you have like the I, this is like P of 1, and this is P bracket, you don't know what yet. And this is Q of 1, and this is Q bracket, you don't know what yet. And so to pick some element in this, some functor, or some natural transformation, or map in polynomial functors, a map from this to this is to choose a formula that takes any P of 1 and gives you a Q of 1. For every P of 1, give me a Q of 1, and for every Q of J, give me a P of I. Give me an element in P of I. So it says, yeah. Yeah.
So on the bottom is the mapping the base, and the top is of that those two cells.
Yeah, it's like, what it's saying is, yeah, a polynomial has two parts. It's got a bunch of positions, and it's got a bunch of directions. And to pick, like in spreadsheets, like sometimes there'll be like blue cells and white cells. At least I've seen this. And the blue cells I'm supposed to fill in, and the white cells are automatically calculated. So phi says, I will calculate the white cells if you fill in the blue cells. Okay, what is it saying? So it says, if you fill in an element of P of 1, phi will automatically fill in an element of Q of 1 for you. That's what this part. For any P of 1, I'll fill in a Q of 1 for you. And now you'll be able to continue and fill in a Q, like a direction, and phi will fill in a direction back in P for you.
So what you're describing here is how to pick a natural, how to define a natural transformation.
Yeah.
It corresponds to these two actions,
Yeah.
filling in an element of positions of P and the direction at that position.
Yeah.
Well, so phi is a natural transformation.
Phi is a natural transformation.
For every phi.
Phi is a formula for taking P positions to Q positions, and then Q directions there back to P directions there. So I think of this like, I think of polynomials a bit like, there's lots of nice ways of drawing them and stuff. But one way you can think of them as like problems and solutions. So each position is like a problem. They're sitting there, I have a problem. There's lots of different problems. And the solution type for any problem is the directions there. Here's my problem, what direction can I go? So this would say, okay, I have two problems. I have four problems. This one has three solutions. This one has two solutions. Next one has two solutions. And the last one has no solutions. There's just no way to answer this one. There's three ways to answer this one. And what this is kind of saying is, it's a way of handing your problems from P to Q and getting it's like what I think of as an abstraction. So you take all of so if you think of an abstraction in life, you say, this thing is a square, or this thing's a circle. Now it becomes this, you've taken a real life thing of which there's tons of them, and you just put them all in the circle box. You call them all a circle. But the point is never just to go one way. It's that once you have a circle, you can ask lots of questions about it. You can do lots of things with it. You can roll it. You can like measure its radius. You can do stuff, right? Anything that you can do to the abstract circle should give you something you can do to the actual concrete circle you have. If you could only go one way, you'd never come back. You wouldn't want to do it. So this is It's like, or if you're, let's say this is the outside of a submarine. This is all the ways that your submarine could be in the water, and like, or like what's around you, and this is like what you can do with your submarine. So, so given a way that's something going on in the like around the submarine, you get a vision in your own control panel. Then you make a choice of what you want to do. Now you're the controller of this thing. You give it a choice of what you want to do, and that's returned to the submarine as its as like some action in the real world. You don't have to understand it. This is abstraction. When you're in the control panel room, the bridge or whatever it's called of the submarine, you don't need to know all the details. You want some abstraction of it. Then you pick what to do, and that's sent back to the actual submarine exterior, and like something actually happens.
So the target of the morphism is the abstraction of the source.
Yeah. So the target of the morphism is the abstraction of the source. Yeah. It is an abstraction of the source. It's a way of taking source positions and consolidating them into, some like
Equivalence classes of some
equivalence class of some sort, and then given some direction to go from there, something to do, it gives you a way to do something in the concrete world. I mean, if polynomials are going to be so important, they should mean something like that we're used to. So that's what I think it is. Yeah.
But it's actually in the reverse. It's not taking just into account the choices purely in terms of the abstraction, because it's also taking into account
Where you started.
came from
Yeah,
in
yeah.
the original situation.
Yeah.
How you adapt it to the context of the
Yeah.
original situation.
It's taking into account the concrete particular case you are in.
Yeah.
This map back does not have to be uniform across all possible ways of getting there. Yeah.
It's contextualized.
Yeah.
Yes.
Someone yesterday, I was thinking about doing a functional programming type approach to this, but I don't know if everyone would understand what it is, so I think I won't do that. But okay, any questions about this? So these are the morphisms of polynomial functors. For each position of P, pick a position of Q. For each direction there, pick a direction back home. I said that a little bit too fast, but okay. Okay. So what is a map from, suppose S is a set. I don't really need this thing anymore. Well, okay. Suppose S is a set. What is a map from sy to the s to some other polynomial? Well, we can just write down what this means. To pick something of this type is to pick something of type for every s in S, choose one of these four things. That was kind of annoying. So this is P. Choose one of the four positions in P. And then for every direction there, pick an element of S again. Maybe I should do an easier example than this. So let's do polymaps from, this will be a lot easier. And we'll come back to this one in a second. by to the a. So monomials. Some people want the word monomial to mean what we call representables, something with one position. But in high school, middle school algebra, they would call this a monomial. They would say like they might say this had three monomials, this one, and this one. So I'm going to use high school algebra terms, or middle school or whatever it was. So, okay. So if we calculate this, it says for every S in S, choose a B in B, and for every A in A, choose an S. Or we said we could choose a function from S to B, And then for every S in S, choose, and every A in A, choose an S. But we never use this F again. We just used it once. We never touched F again. So in fact, this is the same thing as a function from S to B and a function from S times A to S. Yeah.
And that S on the second line you just wrote to the right of that one is coming from the exponent on the left.
This one is this one.
Yes, which is coming from the exponent. in
That
S,
one.
but
Yeah.
Yeah.
One thing I forgot to say is like I want to say two things. I want to describe what that thing I just drew was, which I'll get to in a minute. That's like what's waiting for us. I then want to I want three things. I want to say what this was all about. Then I'm going to get back to what this was all about. But first, I want to come back to this.
Off the stack.
So I have to go backwards. I'm sorry about that. This map from P of 1 to Q of 1, these are both functors. P and Q are functors. And this is a map from P of 1 to Q of 1. That is, in fact, phi 1, the component of the natural transformation. Phi is a natural transformation. And it has components. For every set x, there's a function called phi of x from P of x to Q of x. So in particular, there's one from P of 1 to Q of 1. And this is it. This is the one from phi of 1 to Q of 1. P of 1 to Q of 1. This part is I'll sum over phi of 1, taking P of 1 to Q of 1. Yeah. And then for every, I want to write this part as phi sharp. The thing that's here that goes from I guess I just need to show you. I don't know how to say this very well. This will be phi of 1, and this will be phi sharp. Yeah. Sorry, I feel like I'm butchering this right now. This is phi of 1, and this is phi sharp. Why I call it phi sharp? Okay. Boy, okay. So we have P of 1, and for every element of P of 1, we have P bracket blah that gives us a set, right? And we have Q of 1, and for every position there, we get Q bracket blah that gives us a set. So phi of 1 is here. And phi sharp is a natural transformation like that. It says, given anything here, I can get a set, or I can get another set. I can either get Q bracket, so phi sharp says, phi sharp sub I. If I have any I in here, then I know I get a function between this set and this set. It goes from Q bracket phi 1 of I to P bracket I.
So I don't know if this is helpful, but that's like the delta of the constants.
Yeah, it's a little.
P1 and Q1 are schemas.
Yeah. For people who like.
Yeah, I don't know if that.
For people who like categorical databases, this could be called a schema. This could be called an instance. This could be called a schema. This could be called an instance. This would be a functor, very boring schema, and this would be the delta. Oh, no, it's not the delta. What? No. The delta would be, no. It wouldn't be the delta. That would just be the way of taking this and composing it with that. So, okay. Yeah,
So
sorry.
I've never understood that notation with a big arrow going that way. What does that say? First of all, I'm
Yeah.
trying to understand, what does that mean that you have a big arrow coming from one side of the diagram?
Do you see this as a category? So what this means is when you see this,
Yes.
you're supposed to think
Okay.
that one direction through this diagram
Yes.
is on the right, is on the source of the arrow, and one direction through this diagram is at the target of the arrow. Do you think this one or this one is at the source of this arrow?
So I would think the arrows, the one on the left-hand side of the arrow is probably that one, and the one on the right side is probably that one.
Yeah.
But,
So it's always a little bit confusing. It's
Yeah.
probably this one, and it's the one. It's yeah.
so why how
it's
is
this
it
one.
different from writing a check mark or a little?
Because
thing
it's
that
a
shows
map.
commutes?
This does not commute.
Okay.
If it
doesn't-
commuted, then it would be what Peter was talking about with delta migrations from databases. But if you don't know what that is, don't worry about it. If this commuted, then it'd be a fact.
So it's
But
a
this is
natural
additional data.
transformation
This is additional data. It's a natural transformation between two functors from P of 1 to set. One of them is P bracket blah, P bracket.
Yeah.
The other is Q bracket phi 1 of blah. Q bracket phi 1 of
Okay.
blah.
Sorry. So okay, I'm having a neuronal misfunction.
Okay.
A dysfunction.
Okay.
So sorry. Why are we mapping into
Set.
set?
Yeah.
I mean,
There's just all these different ways of representing polynomial functors, and I think they're important to get at. But I know I'm distracted. Like there's so much on the board right here, and we're all over the place. So I apologize about that. So you're asking, why do I have this data, or why are we viewing it this way?
I guess okay. So P, like normally I think of P bracket I, like P bracket bar. Okay. Because there's a fill in the blank there, you think of it as a functor.
Yeah, I'm thinking of this as a functor now, which is pretty weird. Like that's not how we've been thinking of it
It's
the rest of the day.
funky thing.
It's funky, yeah. This is a bit of a weird way of looking at things, but it is still,
It's a set-valued functor.
Yeah.
it's still a
It's
set-valued
discrete
functor.
category into set.
It's,
Yeah.
yep, but
Yeah.
until just now, we were thinking of these as summands and these as exponents and stuff,
Yeah,
but
exactly.
now
I
we're
thought
kind
it
of
was a set, but I can't even see what it is. My eyes are so bad. So
here.
it's P. That's a dash.
That's a dash,
not an
yeah.
I.
Yeah,
Okay.
yeah.
Okay.
But what I'm confused by is that P bracket blah takes an element of a set, not a set.
It takes an element of yeah, it's a functor. So it takes any object here or any element of this set
Oh.
to set. It gives it a
If
set.
you're thinking
Yeah,
about,
nice.
If you're thinking about P of 1 as a discrete category,
Yeah, if I'm thinking of P of 1 as a discrete category, then I could think of this as a functor. It's a little like, yeah, this is just an alternate formulation of what a polynomial is. There's a way of thinking about polynomials as these pictures here and these pictures here.
Unnecessarily kind of like.
But I just wanted to show you this because
But it is.
this notation is useful. I just wanted to show you this notation. And it can be useful to think of things this way, but maybe it wasn't worth it. The point is that like I'm sometimes going to write phi and phi sharp. And that's one way of viewing where they live.
But this actually makes the lens thing, I don't know, categorical. I don't know.
Yeah.
It kind of expresses the lens structure
Yeah.
as a thing that's
Yeah.
has
That's
to do
true.
with functors and natural
Yeah.
transformations.
So here, phi1 is a functor.
Phi of 1 is, here phi of 1 is a
But
functor.
most of the time, we think of phi1
As a function. Yes. Yeah.
This kind of punning going on.
Yeah. Yeah.
But it is a functor.
It is a.
It's a functor between discrete categories.
It can
It's
be.
promoted to a function.
Yeah, this was a bit of a, probably pedagogically not great, but maybe the struggle to get it right is still worth it. Sorry for those who, I'm just going to put this in some kind of like,
You can dream about it tonight.
yeah, you can dream about this. No,
All
it's
functions dream of functions.
being functors. Okay, so let's get back to, this was just for notation, because I'm going to need this notation at some points. And you can ask about it, and hopefully it'll make sense. And okay, so we were trying to investigate this thing, because we're trying to get towards dynamical systems or machines. And so we have two polynomial functors on the board, sy to the s, by to the a. And we calculated just from this stuff that map, or natural transformation, from sy to the s to by to the a is a choice of map from s to b, a function from s to b, and for all s and all a, an element of s, which is a function from s times a to s. And we took that upstairs there, and that's where we were. And we were trying to look at that as a, what does that do? And so what this does is, like, we're going to call elements of S states. We're going to call B output. And we're going to call A input. And then given that, that terminology, we're going to see if these things make sense. So we've got this machine. So phi is a machine with states S. It outputs, for any state, it outputs it outputs A's and inputs B's. Oh, no. It outputs B's and inputs A's. But why? So what does it really do? So given, what I meant is, given a state, it produces a readout, phi 1 of S. So it produces some output. And then given, when further given an input, and we still have the state, it updates the state. Do you see how we did? Do you see how we didn't? So Peter just said we curried.
You labeled phi sub s.
Because I wrote phi sub sharp s. And back here, though, we see that we didn't actually, like in the most native way of thinking about polynomial maps, we didn't have to write s twice. We just wrote s once. For every s, we get a b, and then for an a, we get an s. We didn't have to, like, over here, we first read out, and then we take in an s and an a and get an s. But we already kind of had the s. I don't know if that made sense or matters, but
I'm not sure what you're.
not too important. It's just like I seem to like not. Over here, I asked for s and an a to get an s, but I already had this s waiting for me. And I used it.
Oh, I see what you're saying. Yes.
And like,
so you copied s somehow.
it feels here like I copied s.
Yeah, it does. Yeah.
But that's because I did a distributive law. Originally, I just had an s, and then I got a b, and then I took in an a, and I got an s.
Yeah.
So either way to look at it is fine. I tend to like this one more and more these days, but yeah. But there's good reason to look at this one too. It can be very helpful. Each representation can be helpful in different times. So this is like a machine. It's got some number of states. Like you're a soda machine. And you've got several states, like $0 input, 25 cents input, 50 cents input, blah, blah, blah. And output, you can say, like, deliver a Coke or deliver money back or whatever. And so someone's just interacting with you. And like at any given moment, you like print something to the screen or drop out a Coke or whatever, and they like press buttons at you, and you update your state, and that's just what's happening forever. So like you could have lots of states: state 1, state 2, state 3, and like, you know, let's say we did 3 y to the 3 to happy medium, sad, y to the LR. Okay, so then someone gives you an R and you get happy or something, and you're originally like this, and then they give you a L and you go there, or they give you an R and you go there, and then here they give you an L or they give you R or something. Which one needs an L? Oh yeah. Okay, do you believe that I've drawn that this whole thing is an example of a polynomial map?
Seems like it might be.
Yeah. Yeah? Okay. Because it says, given a state, I can read out an element of B. Okay, that's what's drawn there. And then, given either L or R, an element of A, an input, I can move to a new state.
So you could have drawn, I don't know, like two readouts and 3 states and.
What?
So you could, basically, that doesn't have to be a
You're saying this-
bijection between 3 and the interface.
Oh,
Right.
oh.
Yeah, it could have been two types of happy and sad, or
Happy and
Yeah,
sad,
yeah.
Or 4. There you go, yeah.
Yeah. Okay.
Yeah.
Okay.
Could have been 4, could have been 12.
Yeah. Sorry about that. Coincidences are usually not what I mean to do. So yeah, this had 3 elements. This had 3 elements. That was a coincidence. So I made this happy so that you would see that I didn't have to use all of these.
Yeah.
I can use them twice. Yeah. I just changed this to be happy so that yeah.
Happiness should abound.
Yeah, happiness abounds. Yeah. Any questions about this? So any state machine you could write this way. Any finite state automata or large automata. If you want non-determinism, we have to talk about another polynomial, which we probably should talk about soon because people seem to like that sort of stuff. Seems like I'm getting a big yes from over there. Okay, well.
this also needs an initial state to be fully.
Yeah, that's right, right. So if we wanted to pick out an initial state, we could pick out a map from there to there, and we get 1, 2, or 3. Yeah. Okay. Yeah. Okay, so this is a map from sy to the s to b, to ay to the by to the a. What would this be? Sy to the s to this sort of thing? Well, every s, what's corresponding to b here? What's the output?
There are different outputs for different sort of situations it can be in, right? So
Here, b was this thing of 1, right?
In that case,
So-
you have different ways of taking.
How many outputs does this one have? 4.
yeah.
Seems like a bunch of people are trying to jump ahead a little bit. Yeah, this one has, so every state gets an output. One, this one, this one, this one, this one, or this one. And then given that output, certain possibilities will come back. If they went to this output, they'll have 3 possibilities that could come, that will change the state. They went to either of these 2 outputs, they'll have 2 possibilities coming back to change the state. So I have, in the book with Nelson, we had sy to the s to like y to the a plus y. Here, every state, this was I imagined like this pond of eyeballs, and every eyeball is either open or closed. If it's closed, it gets no data. If it's open, it's receiving like A inputs. And so there's just a state, and the state just closes the eye, opens the eye, closes the eye. It just thinks, it's like, oh, I'm closed, I'm closed, I'm closed. I'm open, I receive blue. Okay, I'm open, I receive red. It just kind of keeps thinking, closing and opening its eyes, yeah.
But it does have, regardless of which state it's in the right, there's at least one
In this one, it receives like the hum of, when it's closed, it just receives the hum of existence.
So it has like.
Bare existence.
Yeah, it has a clock that
Yeah.
says next.
Yeah, it receives next.
If there were a constant term on the right,
Then it would never continue.
it would never update.
It would never update, yeah.
Yeah.
It'll be stuck, yeah, it'd halt, yeah. So here, in certain states, it halts.
Yeah.
If you had like an A here,
Yeah.
then it would halt in some final state. And you could go walk up to it and read that state. We can talk about how you would walk, like what it would mean to read that state if you want another day. But you'll be sitting there in A and never moving again.
Like if you're running,
Yeah.
if you have no constant terms, it means that your machine can run forever.
Will run forever. Yeah, if you have no constant terms, your machine will run
It will
forever. Yeah.
definitely run forever. And if you have at least one constant term, then it can run forever.
If you have at least one constant term, then it can run forever, or it can
If you have
halt.
at least one non-constant term that can run forever. If you have a constant term that it can stop.
Thank you. If you have at least one non-constant term, it can run forever. Yeah. Thanks, Peter. That's a good point.
So I have a dumb question though about, so with a constant term on the right,
Yeah.
there's a vacuous C# that comes back from.
There's a phi sharp that is applied, that goes from the empty set to this thing. Yeah.
So it's not to say that no phi# exists.
The
it's
phi
just-
sharp, everything, all the math is still the same. It's just
Yes.
that this set is now empty.
Exactly.
Yeah.
But we
If
interpret
this-
it as being no input.
But we interpret it as being no input.
And
Yeah.
later that will be realized when it comes to sort of comonoids and all that sort
Yeah.
of stuff.
Yeah.
Okay. Thanks. It's a dead end path.
Yeah.
Okay, thanks.
Okay. All right. So, yeah. There's also something people talk about a lot in category theory called coalgebras, and that's another way of getting at the same thing. So if you have a functor from set to set, if f is a functor, so given f, an F coalgebra consists of a set S and a function S to F of S. So that's what a coalgebra is. It turns out that if you have S to P of S, that would be for all S in S. Yeah. This is sum over I in P of 1 of the product over D in Pi of S. So to give a function from S to this thing is just to repeat. Let's see, do you guys buy this? To give a function from this to this, well, S is the coproduct of S many ones. So to give a function from a coproduct to anything is to give this many functions from 1 to this. We kind of did this before. So yeah, a function from here to here is like the product over S and S of this thing. And we already said that that's polymaps from Sy to the S to P. This was the product over the S positions of this one, of the sum over the positions of this one, of the directions over the position of this one, of the directions of this one. So there's kind of two ways to express the same thing. And coalgebras are a nice way to express it. They have better, I think they have a nicer sense of morphism. Yeah.
So one thing, so I guess this is one way to approach it. Another way I was thinking was kind of useful. David Jasmeyer's presented that as sort of like you plug S into P, and then you get like these various S to the PI terms for each of them, and so each of them is like that's where you get the mapping down to S, like the map to S, and then you have this map over to each of the output positions or the positions of P. So that's like a pair of those two things.
Yeah.
I don't know if that's helpful.
I don't know.
Yeah, but this is a type of coalgebra. It's different from because
Coalgebras of Cohen.
There's like a Lambeck style coalgebra and
Eilenberg-MacLean style coalgebra. Yeah.
It has like monoid.
Yeah. This is called a Lambeck style coalgebra.
Yeah.
And given one of these, there is a comonad for which these coalgebras are the same as the other kind of coalgebra. There's what's called the co-free comonad. Yeah. Do you have a thing? Okay.
So then when you write, you really mean a function there, right? So, or
Where?
the
This is a this is a set map
That's just a
from
that's
S.
a regular old function.
Yep. Regular old function.
So picking a function from S to P of S is the same as picking a natural transformation from SY to DS.
Yeah.
That's interesting.
Sorry, P of S is. Okay. But the reason coalgebras are a little bit nicer is that then a map between coalgebras is nice. So a map of coalgebras is kind of the obvious thing. So why do I say it's obvious? Well, for a category theorist, maybe you are one, if you had two different objects, if these are objects, that's a coalgebra and that's a coalgebra, and someone said, what's the right kind of morphism from this whole thing to this whole thing? You start to get a sense of what the right thing should be. The right thing is, or the expected thing is, it'll be a function from S to T. But once you do that, P is a functor. And that means P takes functions to functions. So you can take P of F, and then you can ask for that to commute. And so a morphism of coalgebras from this one to this one is a function from S to T, such that when you complete the diagram with P of F, that thing commutes.
We never talked about. We said that P is a functor, but we only ever talked about what it did on sets.
We didn't say what it does on morphisms?
Yeah. Did we?
I guess we didn't. Did we say, yeah. Maybe we, Sophie says we never talked about what polynomial functors do on morphisms. So what is y cubed of x and y cubed of y, capital Y? If I had a function from x to y, do I get a function from x cubed to y cubed? Do I get so if I have a function from 3 to x and a function from x to y, then I just compose to get a function from 3 to y. If I have a function from 3 to x and a function from x to y, then I just compose to get a function from 3 to y. Post-compose. So I don't know whether we ever said what to do on, you're right, in some sense we never said what to do on functions, but we said that we were working in functors, and we're just going to take products of functors and sums of functors, and in some sense, and we're only going to do it to the identity, and so in some sense, if everyone knows what to do with the identity, then they kind of know what to do in general. Yeah. So, okay, so do you guys, yeah. So y plus 1 of 4 of 3. Y squared plus y plus 1 of 2. So if I have 3 dots and 2 dots, yeah, this one will have like this. So this is how many dots are in here. This is how many dots are in here. Where does each dot on the top go? Okay, so we had good luck to us. A, B, 1, 2, 3, 1, 2, 3. A, B. Okay. Where does each dot go? Where does, yeah, there's a lot of dot drawing. Let's just pick a few. Let's pick where this one goes, and this one goes, and this one goes, and this one goes.
I'll do the last one,
Okay, where does this one go?
the one right underneath.
Yes. Okay. So this is dot 3 coming from here. Where does it go? A or B?
B.
Okay.
Wow.
And this is 1, 1. Where does it go? A. This is 1, 2. Where does it go? A. And this is 2, 3. Where does it go? Okay. And does any of them go to BB? Yeah. Okay. Now, why this picture is important, I don't know. It's hard to know why this would ever be important, but poly is like kind of simple and also complicated at the same time. Any questions? Yeah.
For some reason, my inner Sophie that hasn't seen Polly before is super confused right now.
Okay.
I don't know if that's actually true.
Okay.
Other
Are you
people-
asking if anybody is super confused right now?
We do a thermometer thing.
Yeah. Can I see your thermometers?
Or a pause for exercises.
Oh,
Exercises or something.
Well, the function composition thing seems obvious, I guess, but maybe obvious because I've read it.
maybe we should take 5 minutes and people can, everyone just talk to your neighbors, figure out what's going on.
I think it's
Algebras are morphisms in poly, and they're morphisms in set. Yeah.
And they're more, yes. But a map.
These are both sets, and this is a morphism of sets.
Yeah.
Any morphism of sets is a morphism of constant polynomials.
Yeah.
Some people give me some looks. Okay. Yeah.
But then a morphism of coalgebras is a transformation between a morphism between natural transformations, because
Well, between yeah.
morphisms in
So this is a function. This is a function.
Yeah.
This is a function. This is the image of that function under the functor. This is a function,
Mhm.
and this diagram commutes. And there's not. You don't have to think about natural transformations in what I just said.
Yeah, but I'm asking in terms a morphism of coalgebras. What does that correspond to in the language of poly? Because it's a way of sending a morphism in poly to another one.
Just in this very nice way where the behavior is the same.
Yeah.
But it's
Oh.
Right? Because morphism.
I might be able to eventually answer that in some kind. So the question was, okay, I can read this diagram, and that's a map of coalgebras, but what is it just in terms of poly?
Yeah.
And in some sense, this is all in terms of poly because these are all, that's a polynomial. It's actually a set. That's a polynomial. It's actually a set. So all sets are polynomials. All morphisms of sets, all functions are morphisms of polynomials. This diagram is therefore taking place in set or in poly, your choice, and it just commutes. And so everything's in terms of poly. But he's saying, yeah, but what is it? What's a more native way of saying it in poly? And I think for that, I could, there's pretty sophisticated stuff about co-free comonoids and bicomodules and stuff like that that we might get to on day 4, but I wouldn't say it's like super, like, we can't say it more nicely than this right now. Yeah. We're developing technology to make it easier and easier to say easy things. But it takes a lot of work to make easy things easy.
It feels like it's reminding me of what David Myers talks about with charts and one system simulating
Yeah,
another.
yeah.
That,
Yeah, somebody mentioned David Myers and charts, and yeah, these can be, if you know that story, it does fit there. Yeah, yeah. Okay, so what I want to get to, so okay, but it could be that S was empty. There is no states. And so just because you have a map of coalgebras doesn't mean that they're identical. It means that for any start state of S, they're identical. It doesn't mean that every state in T was reachable by 1 in S or is equivalent to 1 in S. It just means if you started in S, the behavior you observe with the S machine will be the same as if you translate to T and observe the behavior of the T machine. If you start in S.
So T could have other things going on.
T could have other stuff going on. We could have a whole, T could have had a whole other, T could have had a T5. Whoops, no. Sorry. Sorry, this was reversed. Here I went from T to S. Sorry about that. So S, in this case, could have had a whole other thing that, like, did some other stuff. Yeah. Or even, like, have a whole other section going on somewhere else. Yeah.
But we take a section of F and map it into part of F, part of like the first thing and map it into T.
Well, I messed up because I made T come, I did it backwards here, so I don't know which one you're asking.
So T goes to S.
T goes to S. Yeah,
Okay.
yeah.
And T selects a part of S.
Each state in T goes to a state in S that will match behaviorally. Yeah. Yeah.
It's not symmetric. So in other words, T could sort of be a simulacron of S, but not vice. Or sorry, one system could sort of mimic the other, but not vice versa.
Yeah. Every state in S,
Yes.
the behavior you observe of it will be exactly the same as if you sent it to T and observed
right,
behavior.
Whereas functions are.
Yeah.
are
Because
single value, right?
because functions are single valued. That could be a way to say it. Yeah.
Right. But the reverse might not be true.
There
or
might-
it could be true.
Yep.
It could
Yeah.
be
If
true.
it
Yeah.
was a-
Yeah. Yeah.
But-
F may or may not be surjective, stuff like that. Yeah. Okay. Great. Okay.
Right.
So, like, we could draw we could write this as like iconography for S to B times S to the A. In other words, S to by to the A of S, or sy to the S to by to the A. These are all synonyms, right? These are all the same thing. But we could draw it like this if we wanted to. And the reason we'd want to is because we're imagining this kind of S state, and that every element of S outputs a B. So what is this? A map from S to B times S to the A is a map from S to B, and a map from S to the A. And that's the same thing as a map from A times S to S. By currying. So does everyone see these 4 things as synonyms? This, and these? No. Okay, which one is different than the others? Is this the same as this?
So how do you move from, so y went away in the top, there's no
I'm
y.
plugging S into this functor. This is a functor, meaning I
you're
can,
evaluating that at S,
yeah,
okay.
and I get this. So 3y to the a is 3 times y to the a. And so if I take this of x, or s, or whatever, it's 3 of x times y to the a of x, which is 3 times x to the a. Can someone say why they're confused?
Introduce the s that you're applying in the second line.
Introduce this s?
Yeah.
What does it mean to introduce it?
Well, just it just comes out.
It's here for any, so given sets, a function like this
Yeah.
is the same thing as a function like this.
The right-hand side is just a set.
Yeah. Okay.
It's weird because this notation is kind of weird. I'm applying this functor to this set. Yeah.
Yeah.
Yeah, the types of the things change subtly there. Like
Are they?
by to the a is a polynomial functor.
By to the a is a polynomial functor applied to s, and I get b times s to the a.
Yeah, that's fine. But
So this one's fine, right? These two being
Yeah,
equal?
Okay. Yeah.
Which one's, is this one fine?
no.
Okay, so that's this one. Functions from s to p, yeah.
Okay.
Wait, I don't get it. Sorry.
We said before that a map from s to p of s
It's just switching back.
is the same thing as sy to the s to p.
He just wrote the.
I'm not sure which one you guys like the best, but these are all the same in terms of the data.
Because you wrote it as a coalgebra in the second line, and then the third line is as a
Map of polynomials, yeah. So for every s, you get a b, and then for every a, you get an s. Yeah. Which is for every s, you get a b, and then for every s and a, you get an s.
I think I need to take pictures.
So can you give the last one on the right again, please?
This one?
Yeah.
Why this is the same as this?
Yes.
Why is this same as this? Yeah, because this means, given an element of s, I get a way to turn a's into s's. Do you believe that s to the a is functions from a to s, right?
Yeah, okay.
So given an s, I get a way to turn a's into s's, but that means, yeah, this is called currying.
Yeah.
Yeah,
okay.
yeah, yeah.
Okay, yeah, I think I get it.
Okay.
And all of these are equivalent to the drawing on the far left.
Oh, and then this is just a drawing. This is just a drawing.
With this
So,
equivalent?
well, these are all the same, and this is the drawing I'm going to give for it.
Okay.
Yeah.
That one, I like that one best.
Okay. So the reason we like this one is because we could imagine doing stuff like this to it. Or we could imagine doing like more interesting things to it. Whatever, right? We could draw weird pictures and make machines that are like sending each other data and updating and all that sort of stuff. And so that's where we want to get to next. Okay, let's get there.
You got rid of the little self loop, but that was visually designed to
Yeah, I just
communicate
couldn't
that
tell.
S is updating.
Yeah, I just couldn't tell if it was like clear enough.
Yeah.
Like it almost looked like an S sub 0 or something, so I was worried about it. But yeah,
Yeah.
it's updating as it's putting out B's, but as A comes in, it's updating.
Yeah.
Yeah. So you could imagine, yeah. Oh no, it's dead now. What did you need about that?
I
Sorry.
just wanted to get a photo.
Oh,
Sorry.
no problem. I think it said, yeah, okay. Okay, so what we need to get here is we need something called tensor for polynomials. So, so y to the a is a functor, and y to the b is a functor. what is this product of this product's a functor. What functor is it? Is it, yeah, what functor is it?
Y to the a plus b.
Y to the a plus b. Because to give a map from a to x and a map from b to x is to give a map from a plus b to x.
And that's what we did earlier.
And I guess we did this earlier, yeah. But surprisingly, you could like make up a symbol called tensor where it's not like anything you learned in high school or whatever. It just gives you this answer. I just made it up. But I didn't make it up. It's called the deconvolution of times. It's like a thing that's like automatic, like is kind of God-given in some sense. So what would you do to like 2y cubed tensor 4y to the 7th? Well, it's like polynomial arithmetic, except you multiply instead of add. And
What does it mean?
but what does it mean? So if I had the sum over I in p of 1, y to the p bracket I, and I tensor it with sum over j in q of 1, y to the q bracket j, you get the sum over choose an I in p, an ij in p of 1 times q of 1. So choose a position in each, and then the directions there are a choice of direction in each. Yeah. Okay. So this is a monoidal product. We'll get to monoidal products more tomorrow, or more monoidal products on poly. But what is the unit of this monoidal product? Like, what could you tensor with?
Y.
Because we want to know.
No, Y.
Just kidding. Yeah. So if you tensor with y, then there'll be just one position, so it won't change the position set, and there'll be just one direction, so it won't change the direction set. Yeah. Okay. So.
Goal, I guess, is what you call it.
Yeah. Okay. So I want to show that if we have. So what does this mean, right? So if we have like, first of all, let me ask a question. What is sy to the s tensor ty to the t? So it's again like a blah y to the blah thing. Okay. Monoidal products mean if I have a map from P1 to Q1 and P2 to Q2, do you believe I would get a map from P1 tensor P2 to Q1 tensor Q2? For it to be a monoidal product, it has to have that property, so I'm basically assuring you this is true. But let's just check it. Maybe you can check it in your head if I walk you through it. So for every position of P, we get a position of Q. P1, Q1, P2, Q2. For every position of P1, we get a position of Q1. For every position of P2, we get a position of Q2. So if I had a position of P1 tensor P2, would I get a position of Q1 tensor Q2? Yes, because I'd take a pair of positions and I would just apply phi1 to one of them and phi2 to the other one and get a pair of positions here. And now I'm sitting here with a pair of directions. And I need a pair of directions back here. But this one gave me a direction for the first one. This one gave me a direction for the second one. So I have that too. Good? Okay. So if I had sy to the s to, Q1 and ty to the t to Q2, then I would get sty to the st to Q1 tensor Q2. So if I had a machine running like turning A1s into B1s, and I had another machine turning A2s into B2s, then I could get a machine turning A1 times A2 into B1 times B2. Like a machine that took in a pair of an A1 and an A2 and gave out pairs of B1s and B2s. Because I just keep track of these two states independently, and one of them would be outputting 1s, and the other one would be outputting 2s. And one would be inputting 1s, and the other would be inputting 2s. And they would just kind of run forever. Or sorry, run in parallel. So you could call this like a parallel product. So if I had a machine in here and a machine in here, like I could take a machine that took A's and gave out B's, and a machine that took in B's and put out C's, and I could tensor these together. It's kind of like I put, I once described it, or we've started describing it as like putting these into a trench coat. Like you imagine two kids standing on each other's shoulders in trench coat. Like nothing's really happening. It's still just two kids. It's not one kid, but like it's a taller kid or whatever. So, so we would just kind of put these two things in a trench coat together. Is this composition?
No, it's not.
It's not composition, yeah.
You would expect, because you
You
want
want
to
it-
just
you
stick
want it
one
to
thing
be-
into the output of the other, but it's
You want it to be.
Yeah,
but
you want, yeah. Okay, so now we've done the thing where we now have these two machines, one here, and we now have them both running without understanding the other. But we want that, like, we want to say that we get a machine where we take in A's and give out C's. And that we do that by, like, plugging the output into the input and going like that. And so but that diagram looks kind of ugly compared to this one. This one's nice. And so what is the diagram itself? What is the type? Like, what if I said I have phi equals this? What is the type of phi? Phi colon what? So phi colon by to the a tensor cy to the b to cy to the a. I want to give you a morphism like this, and we know what this means now. It's a polynomial map. And supposedly there's a polynomial map like this that this diagram is telling us to write. This diagram is syntax. This diagram is syntax for a morphism of polynomials from by to the a, tensor cy to the b. Here's by to the a. I should have written by to the a here. I kind of did. Here's cy to the b. And this whole thing is another box, cy to the a. We're always going to put like, the output here and the input there. Yeah.
Can I ask, again, a silly question about those arrows there?
Which arrows there?
Those three which you were just gesticulating, yeah. Is the bottom one in a different category than the top two?
I should say-
The top two are in set, aren't they?
Yeah.
And the bottom one's in poly? or
Yeah.
something?
These are in set. This one's in poly.
Okay.
Yeah. But there's a functor from set to poly that sends a set to the constant polynomial, sends a to the thing just you would probably write as a. And this is fully faithful, which means a map between sets is the same thing as a map between the corresponding constant functors.
Wow.
A natural transformation, so yeah, you have two functors from set to set.
Yeah.
One is called A. It sends every set in the world to A. And the other one sends every set in the world to B. And you want a natural transformation between them. It's just a function from A to B. Seems like a lot of data to give a natural transformation between two functors. But if they're constant, there's very little data. It's just a function from A to B. So if I have a set, I get a polynomial, just the constant. And if I have a map of sets, a function, I get a map of those polynomials. And so every time I'm writing a set on the board, I'm also writing a polynomial on the board.
You said that once already.
I said that before, but yeah, it's good to, it bears repeating. Yeah,
Wow.
yeah.
What's really confusing about that part, or at least initially, was for me, yeah, is that this lens is just about the wiring. Like
Yeah.
if you were to draw the red box as like a dashed line or something where it doesn't know what is in there,
Yeah.
that's what it talks about. Like it doesn't know about S or T. The thing that
Yeah.
makes you really be able to forget about S or T and have a magic box is a lens from the inner two tensored products to the red box itself. Sorry, I'm just saying that this is just about the wiring.
Yeah. So I want to say that if you give me a wiring pattern like this one, I'm able to give you a term of this type. In other words, a natural transformation between this polynomial functor and this polynomial functor.
Yeah.
So to do that, well, to tensor, when I multiply two sets, I just write them in I just juxtapose them. If that's okay? This really means B times C, A times B. Okay. Yeah. So do you know, to give a map like this, I need to take positions of this to positions of this, and then given a direction of this, a direction of this. So I need to give a map from B times C to C, and a map from B times, so given that position and a direction, I need to get a new direction. Yeah. So to give phi, I need to give a function from B times C to C. The idea is that B is the output of the top box and C is the output of the bottom box, or whatever, and we're supposed to be getting an output of the big box. What output should we use?
Projection.
Yeah, just throw away the B. We don't need it for the output. Yeah, so this is just projection. And then given a B, a C, and an A, how do I get an A and a B? Throw away the C. So it's obvious. But somehow this is telling us that to move data from the inner stuff to the outer stuff, you take the outputs and you don't use this one, you just give out that one. Right? You don't use the B. That's why it's being projected away on the output side. And then it says, okay, and if I have the outputs and I get additionally an input, A, I need inputs for these guys, and it says, oh, throw away the C, you don't need that. What did you say?
I think this is the coolest thing about it. It's like a universal translator.
Yeah. So I want to show you this one because it's more interesting than this one. But yeah, questions?
Yeah, so I'm a little bit confused as to the status. Does a wiring diagram always uniquely specify that mapping?
Yes.
Because couldn't one say, well, there's some funky map from BC to C that's not just projection?
Yeah, it's not the case that every map of polynomials comes from a wiring diagram.
Yeah.
But every wiring diagram uniquely specifies a map of polynomials. So let's suppose that we had this guy, it's outputting an A and a B, and this one's outputting a, I don't know, C and a D. I don't know whether to kind of make things, how well, I don't know. So I'll just kill that guy off, send that one out, and send it back. Okay, maybe this is good. Okay, so what is the type? Oh, let's do one more. Okay, is that good? Is that weird enough?
Yes, that's weird.
Okay.
You didn't label, yeah.
And the first input also.
Oh no, E, F, G, H. Okay. What are the types of the internal boxes that we're going to tensor together?
So A, B to the
A, B, Y to the
Y to the A, E?
C, E?
Or C, E, sorry, yeah.
Yep. Tensor.
Tensor C, D, Y to the B, F?
Tensor. So we're multiplying together all the inputs and all the outputs, right? So, and putting the outputs here and the inputs here.
And then H, Y to the 1?
H, Y to the empty product, which is 1. Okay, and what is the exterior box? Outputs.
ACH
Yeah.
to the EFG.
Okay. So this diagram apparently tells us that we can take an A times B times C times D times H. And if we notice, those are all the outputs, A, B, C, D, and H. And get an output of the total box. I'm going to make this G an A. So it's the same type as this other one. Just to make things like slightly more, less, like you don't always have different sets everywhere, right? Okay, so what do you do?
Throw out B and D.
Yeah.
Wait.
A, B, C, D, H. Just throw out the C and the D. Just throw out the D and the B. Just project those out. Okay. And we need a function from A, B, C, D, H, E, F, A. So we took in an input now. We have all the outputs we started with, including A. But we also got 3 new inputs, like a different A. And we know which A is which, right? This is the A from here, and this is the A from here. I guess we don't need either of them. That's kind of weird. I mean, I'm just not using it very well, but I guess it's okay. Sorry. Is this, yeah. Should I change this diagram to make it a little bit more sense, or no?
Keep rolling.
Keep rolling. Okay. I need a map from this to C, E, B, F.
That's the backwards map.
Which is going to say for all of we have all these outputs coming out. A, B, C, D, H. We have all these inputs coming in, E, F, A. And now all of our interior boxes need to be fed. This one needs a C and an E. And this one needs a B and an F. Do we have what we need? Well, we have a B. We have an F. We have a C. We have an E. We have everything we need. And so we can do it. This C was used twice. This C was used here, and it was again used here. And that's because this thing was splitting. This D was never used. Nobody ever asked for D. That's because D was terminated or whatever. This A was never used. This A was used exactly once.
I have
Yep.
a question about
Yep.
this, which is, that's, like, Poly doesn't allow you to express an input just flowing through, because, like, you can't take the input
Right.
in EFA and give it to the
It does let you. You'd use Mealy machines instead of Moore machines. So we could do that. We just would need 2 different syntaxes for boxes. So a Moore machine is A times S to S and S to B. This is called a Moore machine classically. A Mealy machine is A times S to S times B. This allows the input to go straight through. So we could go from A times S to S times A, for example, in a stateless machine. These will be coalgebras. This is a coalgebra this is a coalgebra. This is more. This is all. So, what am I saying? I'm saying this sort of thing will give you a Mealy machine. Given an S and an A, I get a B. Given an S and an A, I get an S. So we could do it. It just wouldn't. We just wouldn't be able to draw it like with the same syntax. We would need like 2 different kinds of boxes. One where it kind of waits before it updates, and one where it like can update immediately. And so we could, like, you know, for research week, somebody could try to make a syntax for mealy and more machines that work together. That'd be a fun thing to try. Yeah. Oh, I wanted to give, yeah. Okay, so a lot of what we've been doing is, what time do we stop today? Or do a next thing?
Totally in an hour.
Okay,
We're already into our proposed break.
I see.
I think you should find a nice stopping place.
Okay.
Or
What we're gonna stop for, half an hour to.
yeah, we probably also don't need 30 minutes for wrap up and what's next, so we could eat into that.
Okay.
If you wanted to go to like, I don't know, like, I would probably stop definitely by half an hour from now.
Okay. So we'll probably stop in half an hour or so, but or we will stop in half an hour. But what I wanted to say is I wanted to give you another polynomial that's not a monomial, and it's called, I call it Lott for lottery. What is Lott? Well, you choose a natural. What the positions are? You choose a natural number, n. And then you choose further a distribution on n. And then you input an n. But I haven't defined this symbol delta yet. The reason I'm telling you about this is it's for stochastic stuff or non-determinism. So delta n is a set. It's a set of distributions on n. It's the set of all functions from n, which is like the numbers 1 through n, to 0, 1, such that when you add up all of them, p of 1, you get 1. So, for example, can someone give me a few elements in delta 2, delta 3?
0.5, 0.25, 0.25.
Yeah, or 1, 0, 0, or
Yeah, 1/3, 1/3, 1/3.
or 1/3, 1/3, 1/3.
So this is like a bar graph, that's normalized.
Sure, or a pie, like
Yeah, or a pie.
With the number of slices is fixed.
Gotcha.
yeah, 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 where the number of slices is not fixed.
It's given by n.
You choose a number of slices, or I call them tickets. So you have a lottery. It's got n tickets. Every ticket has some chance of winning. Maybe they're all uniform, but maybe you have a bad lottery. Who knows? And then, so what is
Somebody wins.
so what is Lott of? So there's like 14 people in this room or something. It would be to give a lottery of 14 people would be to give a choice of tickets. Maybe there's 73 tickets. So we print out 73 tickets. Some of them have higher chances of winning. Some of them have lower chances of winning, but they add up to 1. And then I give every one of you, I assign the tickets to all of you guys. And everybody, yep. And then, yep, and that's it. Yeah, that's it. That's it. Yeah.
So all the tickets get assigned.
All the tickets get assigned to an element of x, of 14. Yeah. Okay, so what is sy to the s to, oh, darn, I don't have composition yet. Okay, well, let's just do this then. Let's just do this. Okay, so here, I don't know what this will do because it wasn't what I was planning, but we'll see. So here, why don't you think for a while what one of these coalgebra, this is a coalgebra, Lott is a polynomial, I'm allowed to write this. This is a set, this is a set, everything's fine. So what is one of these dynamical systems? It's got a set of states. What does it do?
The state corresponds to one setup of the lottery.
Yeah, given a set, given a state,
Given a state, you have some like
lottery is created.
lottery. A
Yeah,
lottery is created.
yeah. And then? what are the inputs of that lottery?
The winning.
A ticket is chosen,
Chosen.
and the state is
Yeah.
updated.
Yeah.
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 So this is a machine that has a bunch of states. Every state is assigned a lottery,
Yeah.
and then given a choice of ticket, it updates. So this is just some stochastically updating. Maybe every state is assigned 1/3, 1/3, 1/3. And like with 1/3 chance it updates, you could, yeah. So we have, I bet Sophie could draw this better than me. You have S1 and S2 and S3, maybe S is 3. And like with 50% probability you go there, and with 25% probability you go there, and with 25% probability you go there, and this guy with 100, with 90% probability goes there, and 10% probability goes there, and this guy, with 50 and 50 goes there or there. So this guy was given a lottery on 3. So it was given like 3, 1/2, 1/4, 1/4. This guy was given a lottery on 2 with 0.9 and 0.1. And this guy was given lottery on 2 with 0.5 and 0.5.
And so you get a winning number, and that can go to a state with a new type of lottery setup.
This is the entire, I drew one fee.
Okay.
Here is fee.
What does a state update correspond to?
Yeah,
Like, what,
In all of these things, map from SY to the S to P, we'll take every state and give a position, which is like an output, and then given an input, we'll update the state. Here, the output is what lottery you were on. I output a lottery. This one, S1, phi of S1 is the lottery 3, 0.5, 0.25, 0.25. And then, as always, when someone like gives you back like what to do, someone gives you an input, right? We're always like waiting for inputs. Well, here the inputs are what ticket was chosen.
What is the,
And from that, you update the state.
what is the position and direction on Lott?
The positions of Lott, a position of Lott is a pair, is a lottery. A position of Lott is a set of tickets and the distribution or likelihood of each ticket,
Okay,
adding up to 1.
and what's the,
And a direction is a choice of ticket. Which ticket is chosen?
okay.
So these transitions, like from S1 to S2,
Yeah.
does that, so for each state you have a lottery setup, you said.
I just call it a
Like
lottery.
one.
Is it okay to call it a lottery?
Yeah, lottery. And then you get a particular winning ticket.
Yep. And that's your
that-
input.
And then that will dictate the new state.
Yep.
So like the 0.5 could have won the lottery,
Yeah.
in which case you'll go to S2.
Yep.
The crowd goes wild.
Wow. Goal?
Well, it's not only goals,
It's
it's
a-
like 100 goals.
Oh, wow. We just scored 100 goals, guys. Okay, cool.
Okay.
Yeah. Yeah.
and so then to like close that loop, then to like actually get the lottery to like the distribution that you're able to choose to like then pick a ticket, you would need to like feed that. You would need like another.
We would need a Coalgebra. Yeah.
Yeah, you would need
Yeah.
another one to stick on the end that like gives you the mapping that corresponds to going from lottery to chosen ticket.
Yeah. Yeah. Yeah.
Which is,
I'm confused as to where, like the N in the lottery has nothing to do with this, with S,
Uh,
right?
yeah. S is the states.
Yeah.
Every state is assigned a lottery, and given a ticket, we get a new state.
Right.
so it is influenced, like when picking.
Once we have phi, the
Yeah.
state is influenced by the lottery.
Yeah.
But before it, as usual, the set of states was just ready for action. Whatever interface you put it in, with it, whatever machine you used,
Yeah.
that's what causes it. Yeah.
So the states is just like you have a large number of states, it's going to give you more granularity as to how the distribution of tickets
Yeah.
changes.
Yeah.
But I mean, so the distribution of tickets is then, the input isn't deterministic. You said that this was supposed to be stochastic? Like, based on the probability density?
If you looked at this and I didn't tell you where it came from, you would say this was a stochastic dynamical system.
Yeah. Yeah.
The fact that it comes from this shouldn't change that perception. Now, why you think of this as dynamic is because you have in your computer some really good coalgebra of Lott.
Yeah.
I think I'm getting that. I'm not sure if I'm getting that right. There's some. A lot of people are asking in their minds, like, who's choosing tickets?
Yeah.
Like, someone gave us this thing, and we're like, well, where are these choice of tickets coming from? And like, what is actually rolling dice in the universe? And that question is a little bit interesting. My mind is telling me that, but I'm not able to endorse it or check it right now, that like there's this really good coalgebra of Lott, or where over time it will always like give you, let's see, what am I talking about? Yeah, let me come back to you on like how you get these lottery tickets to be chosen. I'll have to do that, like it'll take me like 5 minutes of alone time of like why this one would be chosen 9 times more than this would.
Yeah.
Because like a bad guy, somebody, let's say you had a map from Lott to Y.
Yeah.
Then for every lottery, you would be choosing one ticket. Well, which one would you choose? I don't know, the highest one?
Yeah.
So that's a bad one to choose.
Yeah.
So what should you do to choose lottery tickets? I remember. I think it's that's what it is. Whew. Okay, we're not ready for this yet, but like one of their inside of this is like a really good coalgebra that says, and we're not there yet, so I can't tell you what this means, but they're like the feeling that lotteries are supposed to choose this 9 times more than this can be cashed out here.
Oh, goal.
Nice.
Yeah.
All right.
Not for me.
Well, we'll get there.
Yeah.
The feeling that this should be chosen 9 times more than this is the feeling you want to have understood. And we need.
And how does that have to do with directions?
And how does that have to do with directions?
Yeah, because now I just have arrows labeled 0.1, 0.9.
Yeah. How do you actually make this happen, right? Yeah. Well, I mean, we could do it. We could go on to that right now. It just we'd have to change tack. Yeah.
Talking about, like, what's
So what are we talking about?
what is this feeling?
Someone wrote like this data on the board. This data comes from one of these. They can draw this picture. This is exactly one map from 3y to the 3 to Lott.
Yeah.
But someone's like, how are you choosing that this happens 9 times more often than this? Like, what actually chooses tickets?
I mean, it's going to be defined by your delta n set, right?
Yeah, but who's going to choose the tickets? Delta n set?
I don't know. But
So some people aren't wondering the same question as other people. Yeah.
Like, my sense is I don't care about that. This is just a
Yeah, so some people don't care about
what
this.
happens if you
Yeah.
have this lottery. That's
Yeah, this is the entire data of the thing.
If
Yeah.
you wanted to run right up.
Yeah, let's say you wanted to run this.
Yeah, like give a little terminal program that you choose a ticket and then it.
No, something that chooses tickets for you, right?
Yes, chooses winning tickets.
Yeah,
And
yeah.
you choose a ticket back and whatever. And it tells you whether you win or I don't know.
No, you choose a ticket and you get updated and move through this diagram. You're like, whoa.
And then choosing a ticket represents kind of taking a random step in one of the
Choosing a ticket
directions
is-
along the
yeah.
chain weighted by the probability.
Yeah, that's right.
Yeah.
Okay. So where are we? What do people want to see? Do you believe that for any wiring diagram I could write, you could turn it into a map of polynomials?
Can you give a polynomial map which cannot be a wiring diagram?
Yeah. First of all, 3y to the 3 to y plus 1 isn't a wiring diagram because this isn't a monomial. But you mean one where this is a monomial?
Yeah.
Yeah. So here's how you do it. The map here consisted of two maps, two functions, and they were always, yeah. I wish I'd, yeah. And what happened was every single input was either duplicated. It never turned out to be duplicated for us, but was either duplicated or thrown away. But what if I didn't do that? So let's see. I'll try to do it. So 2y to 2y by 1 maps to 2 and 2 maps to 1. The thing that takes this output and does not send it directly there, but switches it. How would you draw that it switches it? Yeah. So not every map of polynomials from this to this will be a wiring diagram, but there's way, way more. There's like exponentially more actual polynomial maps than there are ones that can be written with wiring diagrams. Does that make sense? Okay, why don't we stop for the day